Hi everyone, welcome back to PolyCloud YouTube channel. In this series, we are learning everything you need to become a Red Hat certified system administrator, that is RHCSA. Whether you are just starting with Linux or preparing for certification exam, this video will guide you step by step, completely free of cost. In this complete series, we will cover understanding and using essential Linux tool, managing software and system services, configuring storage and file system along with managing user group and network and security and a lot more. Everything will be explained clearly with hands-on demos. This is 100% free end-to-end learning series, and I will bring many more such courses on Linux, Azure and cloud technology in coming months. So please support the channel by subscribing and helping us to reach our first 1000 subscriber goal. It really motivates me to keep creating free learning content for you. Currently, Azure 104 series is going on the channel, and also this Red Hat series is going on. So let's get started and master Linux one topic at a time right here on PolyCloud.
Welcome to this course on managing files. This course provides essential skills for navigating and manipulating files within a Linux environment using the command line. From basic file operations to advanced search, permissions, and compression techniques, mastering these tools is crucial for effective system management and day-to-day Linux administration tasks. In this course, we will explore the concept of Linux file systems, including their structure, role, and real-world examples. Then, we will learn how to implement and navigate the Linux file system efficiently. Next, we will learn pattern matching and redirection techniques to manage input and output. We will also explore the differences between soft and hard links and their practical use cases. Next, we will configure, manage, and locate files using essential command line tools. We will also learn file compression and archiving techniques to optimize storage. Finally, we will perform file content analysis to extract and interpret data from various file types. Imagine your Linux system as a large library. Every book, notebook, and folder in that library must be placed on a shelf in an organized way. If not, things will get out of hand. In the world of computers, the file system is the shelf that keeps everything in order, allowing the system to find, read, write, or delete files without confusion. In Linux, and especially for RHCSA learners, understanding the file system is crucial because nearly every task, from managing files to handling disks, depends on it. Let's begin by defining what exactly a file system is. A file system is a method used by the operating system to organize and store data on storage devices, such as hard drives, SSDs, or USB drives. It decides how files are named, stored, and retrieved. The operating system requires a file system to manage all the files, much like a library needs a catalog system to organize its books. The computer wouldn't know where your files are or how to open your programs without it. What makes Linux file systems different? Linux uses a hierarchical file system, which means everything starts from a single root directory / just a forward slash. From there, all files and folders branch out in a tree-like structure. So, whether you're dealing with system files and / etc., user files and / home, or temporary data and /tmp, they all fall under that single /root. This is very different from Windows, which uses separate drive letters such as C, D, and so on. For example, in Linux, the main system configuration files are in /etc., user-specific files are in /home, /username, and logs are stored in /var/log. This structure helps admins keep things organized and predictable, which is why it's part of the RHCSA exam. Now, let's compare it with a real-world example. Let's say you work in an office where every department stores its documents in labeled cabinets. Each cabinet has shelves, and every shelf has folders. Now, think of the office building as your storage device. The cabinets represent partitions, the folders represent directories, and the documents represent actual files. It would be hard to find anything if there wasn't a way to keep track of where each document is and what it's called. The file system gives you that kind of organization. It ensures that you don't accidentally overwrite documents. You can find files quickly, and you know which folder a file belongs to. In Linux, the file system also controls permissions, which are locked in drawers. Everyone can open some files, while others are restricted to specific users or the administrator. These permissions are part of the file system's job. Now, let's look at some common Linux file systems. There are several file systems used in Linux, but for RHCSA, these are the key ones you should know. Extension 4. This is the most used file system in RHEL-based systems. It's reliable, fast, and supports large files and partitions. It's what most installations use by default. XFS is another popular option in Red Hat. It's suitable for handling large amounts of data and is known for its high performance. RHEL often uses XFS by default for newer systems. Each file system has its strengths. For example, if you're setting up a server to store large amounts of log data, XFS might be a better choice. But for a regular desktop or basic server, Extension 4 works well. Why is this important beyond exams? In real-life Linux system administration, the file system is everywhere. Whether you're creating new users, backing up data, managing logs, or checking disk space, the file system is involved. If a file system gets corrupted, you could lose critical data. If it's not mounted properly, the service might fail to start. That's why Red Hat expects you to be comfortable working with different types and understanding how they function. The Linux file system might seem invisible, but it's always there, keeping your data safe and organized. Like the shelves in a well-managed library, it helps everything run smoothly. Whether you're formatting a new disk or checking permissions on a file, the more you understand how the file system works, the better you'll be solving problems and managing Linux systems. Screen. To learn more about the available options for the tree command, type the following command. Man tree. Enter. This opens the manual page for the tree command, displaying a list of useful options you can use to customize its output. Some commonly used options include -a lists all files, including hidden ones. -d lists directories only. -l follows symbolic links. -f displays the full path for each file. -x limits the tree to the current file system. -L specifies the maximum display depth. -R enables recursive listing. You can scroll through the man page to explore more. When you're done, press Q to exit the manual page of tree. Now to view the tree structure of the etc directory, type the following command. tree/e, then press enter. The output will display a hierarchical view of the contents within the etc directory. And with that, we've successfully covered the most commonly used Linux command for file system navigation in Red Hat Enterprise Linux. In this demonstration, we'll learn how to use wildcard-based file name matching and apply input-output redirection to control and combine command output. First, click on the Activities tab located at the top left corner of your screen. Then, find the terminal icon at the bottom of the act and click on it to launch the terminal. Let's begin with using wildcards for file name matching. There are three main wildcard operators used in Linux to match file or directory names based on patterns. The first wildcard operator is star. The second wildcard operator is question mark. And the third wildcard operator is square brackets. Let's look at each one. The star matches any number of characters. It's often used to list all files in a directory or to match files with similar names. The question mark matches a single character at a specific position in any file or a directory. The square brackets are used to match any one character inside the brackets. These wildcard operators make it easy to work with multiple files at once by specifying flexible search patterns. Let's now illustrate the use of the star wildcard operator. Type the following command. ls/etc/star.conf. Then press command lists all files in the etc directory that end with the .conf extension. In the output, you'll see various configuration files such as locale.conf, resolve.conf, sudo.conf, and many more. Let's now clear the screen. Now let's explore the second wildcard operator, the question mark. In the terminal, type the command ls/home/john/test/test .text. Then press enter. This command looks for files that match the pattern test .txt, which means any file that starts with test as a single character and ending with .txt. In the output, you'll see files like test1.txt, test2.txt, test3.txt, These files are all located in the test directory under the John user's home directory. Let's now clear the screen. Now let's use the third wildcard operator, which is square brackets. First, we need to set up the environment by creating 6 files. In the terminal, type the following commands one by one and press enter after each. Touch file1.txt. Touch file2.txt. Touch file3.txt. Touch file4.txt. Touch file5.txt. Touch file6. These commands use the touch command to create 6 empty files named from file1.txt to file6.txt. Now clear the terminal screen. Now type the following command to match files using the square bracket wildcard. ls file open square bracket and type 1-6 close square bracket then .txt enter. In the output, you can see that all 6 files from file1.txt to file6.txt are listed. The pattern 1-6 inside square brackets matches any single digit between 1 and 6, making it an efficient way to target multiple files with similar naming. Clear the terminal for a fresh view. Now let's explore input and output redirection in Linux. There are 3 basic types of redirection you should know. First is the output redirection, denoted by the greater than symbol. This sends the output of a command to a file instead of displaying it on screen. If the file already exists, it will be overwritten. Second is append output, represented by 2 greater than symbols. This adds new output to the end of an existing file without erasing its current contents. And lastly, we have input redirection, denoted by the less than symbol. This takes the input for a command from a file, rather than typing it in manually through the keyboard. These redirection operators are powerful tools that let you control how data flows into and out of commands and files, making your work in the terminal more efficient and flexible. Now let's try some input and output redirection commands in Linux. First, we'll redirect the output of a command into a file. Type the following command: ls-l/etc greater than sign etc_list.txt. Press enter. This command lists all files and directories in the etc directory along with their permissions, owners, and timestamps, then saves the output into a file named etc_list.txt. Now type ls and press enter. You'll see that the file etc_list.txt has been created. To view its contents directly in the terminal, type the command cat etc_list.txt. Press enter. In the output, you'll now see detailed information about the contents of the etc directory, such as security, SE Linux, and others along with their permissions and modification timestamps and other details. Let's again clear the terminal screen. Now let's append the output of a command into a file using the append operator. Type the following command in the terminal: df-h insert append operator, denoted by 2 greater than sign. Then type disk_report.txt. In this command, df-h shows disk usage in human-readable format. Append operator appends the output to the file named disk_report.txt. Now press enter. To verify that the data was saved into the file, type cat disk_report.txt. Then press enter. You'll see the disk usage data from the df-h command stored in the file. Now let's append more information to the same file. ls-l insert append operator, then type disk_report.txt. Then press enter. This appends the detailed list of files in the current directory to the existing disk_report. Now clear the terminal screen. Let's view the updated file contents. Type cat disk_report.txt. Then press enter. You'll now see that the file, first the output of df-h, followed by the output of ls-l. This is how the append operator keeps adding new command output to the same file without erasing the previous content. Now clear the terminal screen. Now let's use the input redirection command. In the terminal, type wc-l, then insert less than symbol /etc/passwd. This command uses wc -l to count the number of lines in a file. By using the less than symbol, we redirect the contents of /etc/passwd as input to the wc command. Enter. In the output, you'll see 36, which means there are 36 lines in the passwd file, typically representing user accounts on the system. To combine command outputs, you can use the pipe symbol. Let's try an example. Type the following command: grep/bin/bash/etc/passwd, insert pipe symbol cut -d:\f1. Here's what each part does. grep/bin/bash/etc/passwd filters all lines in the password file that contains /bin/bash, which usually identifies users with login access. The pipe symbol takes the output of the first command and sends it as input to the next. cut-d:\f1 splits each line by the colon and displays only the first field, which is the username. Press enter. In the output, you can see usernames like Root and John. These are the users with /bin/bash as their login shell. And with that, we've successfully covered how to use wildcard-based file name matching and apply input-output redirection to control and combine command outputs. Let's start with the idea behind inodes. Think of an inode as a tiny information card for every file on your Linux system. Just like a library book has a catalog card with details such as the author, date, and location on the shelf, an inode holds information about a file, including its size, permissions, creation date, and where it resides on the disk. It does not store the actual file name. Instead, it stores the necessary metadata that the system needs to handle the file. Every file in Linux has one inode, which is identified by a unique number. The file name, on the other hand, lives in the directory structure and points to the inode. So, even if you rename a file, the inode stays the same. That's important to remember because inodes are the backbone of how Linux finds and manages files. What happens when you copy or move a file? Let's say you move a file from one folder to another on the same disk. In that case, you're just changing the directory entry, the name, and the location, but the inode stays the same. It's like moving a book from one shelf to another while keeping the same catalog card. But if you copy the file, Linux creates a brand new inode for the copy. That's like writing a whole new book and giving it a fresh catalog card, leaving you with two independent files with different inodes. What is a hard link? A hard link is another name for the same file, not just in appearance, but also in structure. It points directly to the same inode. That means when you create a hard link, you're not copying the file or creating a shortcut to it. You're giving the file an extra name that also connects to the same inode. Here's an example in plain language. Suppose you have a file called report.txt. If you create a hard link to it and name it backup.txt, both report.txt and backup.txt now point to the same inode. They're equal. There's no original and no copy. Both are the same file under different names. If you change the contents of one, the other reflects it instantly because the data is shared. Now, if you delete report.txt, the file doesn't disappear because backup.txt still links to the same inode. The actual data stays alive until all hard links pointing to it are removed. But there's one rule. Hard links can't cross file systems. That means both names must exist on the same disk partition. What about soft links or symbolic links? A soft link, also known as a symbolic link or symlink, is more like a shortcut. It doesn't point directly to the inode. Instead, it points to the file name. It's similar to creating a shortcut on your desktop to a file located deep within a folder. When you open a soft link, Linux reads the link and then redirects you to the original file. But here's the catch. If you delete the original file, the soft link breaks. It becomes a dangling link, meaning it points to a file that no longer exists. So, going back to our earlier example, if you create a soft link called shortcut.txt to report.txt and then delete report.txt, shortcut.txt won't work anymore. It's like having a map of a place that got bulldozed. The map exists, but the destination is no longer there. Soft links can cross file systems, unlike hard links, and they can also point to directories, which hard links generally avoid. Let's now understand how these concepts help you as a Linux user or RHCSA candidate. Understanding inodes, hard links, and soft links gives you better control over how files behave on your system. For example, using hard links can save disk space when multiple references to the same file are needed. Soft links help create easier paths to deeply nested files or for setting up version directories where the current version always points to the latest folder. So, inodes are like ID cards that hold all the behind-the-scenes information about your files. Hard links are additional names for the same file, same inode, while soft links are pointers that follow the file name, acting as a shortcut. Each has its own use, strengths, and limits. Knowing when to use a hard link versus a soft link can make your Linux life much easier, especially when dealing with system configurations or backups. In this demonstration, we will execute commands for managing and locating files. To locate files in Red Hat Enterprise Linux, we use commands like find, locate, which, and type. To begin, click on the Activities tab located at the top left corner of your screen. Click on the terminal icon to open the terminal. First, we will use the find command to locate the httpd.conf file by name. In the terminal, type find/etc-name inside the double quotes type httpd.conf. In the output, you can see the file is located at /etc/httpd/conf/httpd.conf. Next, let's use the find command with the type and size options to search for files based on size. In the terminal, type find/home-type small f-size plus 10 capital M. Then press in the output. You'll notice that there are no files larger than 10 megabytes in this directory. Now let's modify the command to use bytes instead of megabytes. Press the up arrow key to recall the previous command and replace capital M with small b. Command becomes find/home-type small f-size plus 10 small b. Press enter. In the output, you can now see files that are larger than 10 bytes. Clear the terminal screen. Next, we will use the locate command. This command searches a pre-built index, making it much faster than find command. To locate the SSHD configuration file, type the following command in the terminal. Locate SSHD_config. Press enter. In the output, you can see that SSHD_config is located in multiple directories, typically including /etc/ssh/sshd_config and other backup or documentation paths. This is how you can quickly find files using the locate command. Now we will use the which command to locate executable files of installed commands. First, type the following command, which vim, then press enter. In the output, you'll see that the vim executable file is located in /usr/bin/vim. Next, type which systemctl. The output displays that the systemctl command is located in /usr/bin/systemctl. To directly interpret the nature of a command, we use the type command. In the terminal, type the command. Type passwd, then press enter. The output shows that the passwd command is located in /usr/bin/passwd. Next, to check the nature of the cd command, use the command. Type cd, then press enter. The output displays that cd is a shell built-in, meaning it's built directly into the shell for an executable file. Clear the terminal screen. Now let's explore managing file and directory permissions. Start by typing the following command. ls, then press enter. In the output, you can see the permissions for each file and directory. For example, the file disk_report.txt shows that the owner has read and write permissions. The group has only read permission, and other users also have only read permission. For the desktop directory, the owner has read, write, and execute permissions. The group has read and execute permissions, and others also have read and execute permissions. You can check permissions or ownership of any specific file or directory by using the ls --l command followed by the path of that file or directory. Once done, clear the terminal screen. To change the permissions of file, we use the chmod command. Let's try modifying the permissions of file. Type the following command: ls-l, then press enter. In the output, locate the file etc_list.txt. You will notice that it has read and write permissions for the owner, but no execute permission. To add execute permission for the file owner, type chmod u plus x etc_list.txt. Here, u plus x adds execute permission for the user. Then press enter. Let's check the permissions of the file etc. Now, check the updated permissions by typing ls-l. Press enter. In the output, you'll see that etc_list.txt now has execute permission added for the owner indicated by RWX. This confirms that the permission has been successfully updated. To change the group permission of file, type the following command in the terminal: chmod g+w etc_list.txt. Then press enter. This command adds write permission for the group on the file. Now to verify the updated permissions, type ls, then press enter. In the output, you'll notice that the group now has write permission in addition to the existing ones. Clear the terminal screen. To change the file owner, we use the chown command. In the terminal, type chown john etc_list.txt. Then press enter. This command changes the ownership of the file etc_list.txt to the user John. Now to verify the change, type ls-small, press enter. In the output, you'll notice that the main user or owner of the file etc_list.txt is now set to John. To change both the owner and the group associated with the file, we use the colon separator. Type the command chown john etc_list.txt. Then press enter. Clear the terminal screen. Now to confirm the changes, type ls-l. Press enter. You'll see that both the owner and the group of etc_list.txt have been updated. To change only the group ownership of file, use the chgrp command. In the terminal, type chgrp root etc_list.txt. Then press enter. This command sets the group owner of the file to root. To confirm the change, type ls-l, enter. In the output, you'll see that the group for etc_list.txt is now set to root. And with that, we've successfully executed commands for managing and locating files in Red Hat Enterprise Linux. In this demonstration, we'll compress and extract files using the tar, gzip, bzip2, and xe commands in Red Hat Enterprise Linux. The tar command is used to bundle multiple files or directories into a single archive file. To begin, you need to open the terminal. So click on the Activities tab at the top left corner of the navigate to the options displayed below and click on the terminal icon. This will open the terminal window. Now type tar-cvf. The -cvf options represent the following. C is for creating a new archive. V enables verbose mode to display progress. And F allows you to specify the name of the archive file. Next, provide a name for your archive. For example, backup.tar, and specify the directory you want to compress. In this demonstration, we're compressing the httpd directory. So type /etc/httpd. Press enter. In the output, you'll see that everything from the httpd directory has been archived into the backup.tar file. These may include configuration files like /etc/httpd/conf.d, /etc/httpd/conf.d/readme, and many more. Let's now clear the screen. Then type the command to list all the files. In the output, you'll see that the backup.tar file has been successfully created, containing the archived content of the httpd directory. You can explore multiple options available with the tar command by accessing its manual page. To do this, type the following command: man tar, then press enter. Manual. Here are the commonly used tar command formats under Unix style usage section. These include tar-small c to create a new archive, tar-small d to find differences between an archive and the file system, tar-small t to list the contents of an archive, tar-small u to update an existing archive with new or modified files, tar-small x to extract files from an archive. Now scroll down to view example commands such as tar-small cvf etc.tar/etc. This format is used to create .tar archive file from the specified directory. As you continue scrolling, you'll come across many more similar options and practical usage examples. When you're done, press the Q on your keyboard to exit the manual page. Now clear the terminal again. We can compress the archive further by using the gzip command. To do this, type gzip. Next, type the name of the file you want to compress. In our case, backup, then press enter. Now, to check the file type, ls, press enter. In the output, you'll notice a file named backup.tar.gz. The .gz extension indicates that the file has been compressed using gzip. To decompress the file, type gun zip and type the name of the compressed file, backup.tar.gz. Now, type ls and press enter to verify. In the output, you can see backup.tar. This indicates that the file has been successfully decompressed and restored to its original form. Similarly, you can use the bzip2 command to compress the file, which will generate a file with .bz2 extension. So type the following command: bzip2 backup.tar, then press enter. Now to check whether the compressed file has been created, type and press enter. In the output, you'll see the file backup.tar.bz2, which indicates it has been compressed using bzip2. To decompress the same file, type the following command: unzip2 backup.tar.bz2, then press enter. Now type ls command again to verify. Press enter. You can see that the file backup.tar has been successfully decompressed and restored to its original form. Let's now clear the screen. Similarly, we use the gz command to compress the file. To begin, type the following in the terminal: gz backup.tar, then press enter. Now type ls to view the compressed file. Press enter. In the output, you'll see the compressed file backup.tar.gz, which indicates the file has been compressed. That extension confirms that the gz compression format was used. To decompress the file, type the following command in the terminal: gz backup.tar.gz, then press enter. Now type ls, press enter. The output will show the original file, backup.tar. Let's again clear the terminal screen. If you want to combine the tar command with a compression utility, it can be done in a single step. So type the following: tar-small czvf etc_backup.tar.gz/et. Press enter to execute the whole command. This command will archive and compress the /etc directory into a .tar.gz file. Wait for the process to complete, as it may take a few seconds. Once completed, let's now clear the screen. Now type and press enter to check if the compressed file has been created. In the output, you'll see that the compressed file, etc_backup.tar.gz, has been successfully created. To decompress any tar file, type the following command: tar-small xvf backup.tar. Here, -small x is for extract, -small v is for verbose to shows progress, -small f is for file name backup.tar. Press enter. In the output, you can see that the contents of backup.tar are being extracted. This means the file has now been successfully decompressed. Now clear the terminal screen. To verify the extraction, type press enter. In the output, you should see a folder named etc, which was stored inside the backup.tar file. Finally, clear the terminal screen. And that concludes the demonstration of file compression and extraction in Red Hat Enterprise Linux. In this demonstration, we'll use various command line tools, such as sort, Unix, diff, and CMP to perform file content analysis. We'll also use the head and tail commands to analyze file contents within a Red Hat Enterprise Linux system. To begin, you need to open the terminal. Click on the Activities tab located at the top left corner of the screen. From the Options display icon to launch the terminal window. Once open, we're now ready to begin analyzing file content using the powerful CLI tools. We'll use the sort command to arrange file entries in alphabetical or numerical order. So type sort /etc/, then press enter. This command sorts the contents of the /etc/passwd file in alphabetical order, based on the beginning of each line, which typically starts with the username. As you scroll through the output, you'll notice entries starting with lowercase like Apache and Avahi, followed by entries starting with B, such as bin, then continuing with C entries like Cronny and Clevis. Then we can see entries starting with D, like Daemon. The sorting progresses alphabetically through the rest of the file. Let's again clear the terminal screen. Now let's demonstrate the unit command. This command helps remove duplicate lines from a file or input. But keep in mind, it only works on sorted data. Let's see how it works. Now let's create a new sample file named users.txt and insert some data into it. To do this, type the following command in the terminal. echo-small e inside double quotes type John \n, John \nroot, \nroot, \ndemon, \ndora, \nmike, \nlana, \nsarah, \nsarah, \nuser, \ntest, \ndemo, \ndemo, \n. Insert an input operator denoted by 1 greater than sign. Then type users.txt. Let's break down the command. echo-small e allows interpretation of special characters like \n, which stands for a new line. Everything inside the double quotes is the list of users, each separated by \n, to place them on separate lines. Input redirection operator creates the file users.txt and writes this content into it. Press enter to execute the command. The file users.txt is now created with sample user data. Now clear the terminal screen. Now let's open the sample file users.txt we just created. To begin, we'll open a sample file named users.txt, which is already saved in our system. In the terminal, type cat users.t and press enter. In the output, you'll see names like John, root, Sarah, test, and demo, some of which appear multiple times. Now to remove these duplicates, we'll combine the sort and unit commands using a pipe operator. Type the following command. Sort users.txt. Insert a pipe operator denoted by a vertical bar, then type unit. Enter. In the output, each name now appears only once, and the list is sorted alphabetically. This makes the data cleaner, more organized, and easier to read. Clear the terminal screen. Next, we'll use the diff command. This command helps us identify the differences between the contents of two text files, line by line. But before using the command, make sure you've already created two text files for comparison. In my case, I've already created two files named test.txt and test1.txt for this demonstration. Now type the following command in the terminal. Diff test.txt test1.txt. Execute the command. The output displays the differences between test.txt and test1.txt. Lines that are unique to test.txt are marked with a less than symbol. Lines that are unique to test1.txt are marked with a greater than symbol. In this example, test.txt contains lines like, "Hello, John. I'm Mike, your school friend," while test1.txt includes, "Hello, Mike. I'm John, your friend." This line-by-line comparison helps identify exactly what has changed between the two files. To compare two files, byte by byte, we can use the CMP command. Let's start by clearing the terminal for a clean workspace. Now to compare two files named test.txt and test1.txt, type the following command. CMP test.txt test1, then press enter to execute the command. In the output, you'll see a message like test.txt, test1.txt, differ, byte 7, line 1. This tells us that the two files are different starting at byte 7 on line 1. Now, let's explore the head command, which displays the top few lines of a file. By default, the head command shows the first 10 lines, even if you don't specify a number. Type the following command in the terminal. head-n 10/etc/passwd. In this command, head displays the beginning part of a file. n 10 shows the first 10 lines. n/etc/password is the file that stores user account information on Linux systems. Then press enter. In the output, you'll see the first 10 lines of the /etc/passwd file. Each line in this file represents a system user and contains details such as username, user ID or UID, group ID or GID, home directory, default shell. Similarly, the tail command displays the last few lines of the file. By default, tail shows the last 10 lines, unless you specify a different number. Let's print the last 5 lines of a file. To do that, type the following command in the terminal. tail-n 5/etc/passwd. In this command, tail displays the bottom part of a file. -n 5 shows the last 5 lines of the file. /etc/passwd is a system that holds user account info. Then press enter. In the output, you'll notice that it displays the last 5 lines of the /etc/passwd file, which typically contains user account information on the system. This concludes the demonstration, where we performed file content analysis using powerful command line tools grep, wc, cut, sort, unic, diff, and cmp, along with head and tail, within a Red Hat Enterprise Linux system. In this course, we explored the fundamentals of Linux file systems, including their structure, purpose, and real-world applications. Moving on, we demonstrated how to navigate and implement the Linux file system. We also learned to use pattern matching and redirection to control input and output. Next, we discussed the differences between soft and hard links and examined their practical use cases. We also covered essential file management techniques, including locating, compressing, and archiving files. Finally, we performed file content analysis to extract and interpret meaningful data from various file types. In the next course, we will explore help commands and text editing in depth.